Hello everyone. In this section, what we're going to be doing is dealing with another type of transport problem. The difference between the previous transport problem and this transport problem are small but significant. Assignment models are a special type of transportation problem where supply is always equal to 1. Only 1 is supplied. And demand is also only equal to 1. So in this situation, we're thinking of assignments, not homework assignments, but where someone should work, where someone should perform a task, something like that. For example, if Kyung-sung wanted to operate efficiently, one thing they could do to minimize my travel around the school is to assign all of the professors to classes that are closest to where their offices are. That would be an assignment problem. It would be taking the meter distance for each professor from their office to each classroom and choosing mathematically how to minimize travel time. Now, in the real world, it's not that easy, because we have limitations like I teach some classes, Professor Ross teaches others. I teach some classes, Professor Hussein teaches others. However, an assignment problem applied to that situation could minimize travel time. And we're going to see that in today's example. So assignment problems, one more time, are problems where we're assigning someone to a task. Someone or something to a task. We only require one. There is only one available. We're only supplying one. One is only being demanded. So let's look at an example. The Atlantic Coast Conference, which is an American college basketball division, has 4 basketball games on a particular night. The conference office wants to assign 4 teams of officials to 4 games in a way that will minimize the total distance traveled by the officials. So what we're seeing here is they have 4 groups of officials, referees, etc. They need each team to have 1 group of officials. So we have 4 groups of officials, we have 4 games. Seems easy enough. But what they also want to do is minimize the total distance traveled by officials. This was similar to what I said earlier. If you have 8 professors and 8 classes, it's an easy job. But if we want to minimize the average or the total distance traveled by those professors, then we need to use an assignment problem to optimize travel time. That's what we're doing here. So they have 4 officials going to 4 games, and they want to minimize the total travel. The supply is 1 team of officials. The demand is 1 team of officials. That makes this an assignment problem. So supply is 1 team of officials. Demand is 1 team of officials. That is how we know we found an assignment problem. The distance in miles for each team of officials to each game location is shown in the following table. So here we have team, let's change this a little bit. Team A, team B, team C, team D. And we have 4 locations: Raleigh, Atlanta, Durham, and Clemson. This is the travel distance. For Team A to arrive in Raleigh, they have to travel 210 miles. For Team A to travel to Atlanta, it's only 90 miles. So clearly we think it's Atlanta. But Team B is only 70 miles. Team C is only 65 miles. So it becomes more confusing. This gives our total travel time for each route. The linear programming formulation of this model is similar to the formulation of the transportation model, except all the supply values equal 1. And all the demand values at each destination equal 1. So we have supply and demand in both locations equal to 1. So let's do first, we're given the table, but let's look at this in a traditional method. So like a transportation problem, we're trying to minimize z is equal to 210x AR, which is team A to Raleigh, plus 90x AA, team A to Atlanta, plus 180x AD, plus 160x AC, plus, and these represent team A to Raleigh, team A to Atlanta, team A to Durham, and team A to Clemson. That is what we're representing here. This is the first set of possible travel locations. We continue. 100 BX BR plus 70 BX BA plus 130 up 130 X BD plus 200 X BC. And this represents the second grouping. Team B to Raleigh, Team B to Atlanta, Team B to Durham, and Team B to Clemson. We continue on. 175 CXCR plus 105 XCA plus 140 XCD plus 170 170 CACB, XCR, XCA, XCD, 170 XCC plus. So again, the continuation, you can see the pattern. We're simply, when we can solve like this is absolutely possible. If we enter this information into QM, if we enter this information as is into Excel, and we do it properly, the computer will still give us the correct answer. So that's why we're formulating it now, just to see DA plus 65 D. A plus 105 XDD plus 120 XDC. So this completes our objective function. Now, the issue here, as you could see when I was doing it, is the potential for mistakes. If you are entering all of these values manually, it's very easy to make mistakes. It's definitely possible to solve like this, but it's not necessarily the most efficient way. And we'll see that in a minute, because I'm going to now do all of our constraints. So X, AR plus, XAR, which is X, Team A to rally, plus XAA, plus XAD, plus XAC is less than or equal to, not less than or equal to 1. And what this represents is the amount of, or the officials Team A can only go to one of these places. If they go to XAA, then XAR, XAD, XAC must equal 0. If one of these numbers is 1, then the others must by definition be 0. We do repeat that again. X plus XPA plus XPD plus XPC is equal to 1. And this represents official Team B. Official Team B can only go to one place. If they go to more than one place, then it will not equal to 1. They can only go to 1. So that's our second constraint. C3, C4, C5, C6, C7, C8. So C3, we'll do the repeat again, XCR, XCA, XCD, XCC is equal to 1. Here again, this represents all of the possible destinations of Team C. Official Team C can go to any one of these 4 places, but it can only go to one of them. If it's more than one, it doesn't work. They can't be in more places or more than one place at a time. So we have XDR plus, XDA plus XDD plus XDC is equal to 1. Here again, we see that Team D can only go to one place. If they go to Durham, they cannot go to Raleigh. If they go to Durham and Raleigh, it's equal to 2, and that will violate our constraint. That is an impossible scenario. So the first 4 are official. The first 4 are official teams A to D destinations. Now in the second grouping, we're going to come down here. C5 is XAR plus XBR plus XCR plus XDR equal to 1. This represents the team of officials A plus the team of officials B plus the team of officials C plus the team of officials D going to Raleigh. Team A going to Raleigh, Team B going to Raleigh, Team C going to Raleigh, Team D going to Raleigh. Only one of those teams can go. If it's more than one of those teams, it doesn't work. It violates our constraint. So we're going to do that 3 more times just to show you. And if we were to do this, if we were to input the information like this, it would work. It's not impossible. It's just not efficient. Because this is a specialized problem, we're able to use specialized tools in our management software. So we go X AA plus X BA plus X BD plus X BC equal to 1. And that's what we see here. AA, BA, BD, BC equal to 1. So each of those, CA, sorry, wait a second, AA, BA, CD, DD. What am I doing? That's my mistake. C, A, D, A. These represent all of the 4 possible teams going to Atlanta. Only one can go to Atlanta, but that's what this represents. If more than one goes to Atlanta, or if none go to Atlanta, that is broken. It must be only one. If none of the teams go, it would be 0 plus 0 plus 0 plus 0, and that does not equal to 1. So C7, we have X AD plus X BD plus X CD plus X DD equal to 1. And here again, now we're talking about who is going to end up in Durham. So we're almost done. We'll repeat this one more time just to show that it is possible to solve in this manner, but it's not an efficient manner. So these represent destination requirements. Each destination requires only one. So finally we have XAC plus XBC plus XCC plus XDC equal to 1. And here again, we have this scenario where all of these situations are equal to 1. So what we've done is we've formulated in the traditional format here. This is the format that we require. This is how we format it to show there are multiple ways. There are no secrets here. We're just using convenient setups to allow ourselves to take advantage of the power of the computing software. So what we're going to do now is I'll pause the video for 1 second while I prepare QM. All right, welcome back everyone. As can be expected, our solution here in QM will be relatively simple. Because as I said again and again, transportation problems are severely limited in when they can be applied. That's a problem, but it also makes things much easier when we are applying them. In the scenario in front of you, this is a very simple problem to solve. There are only 4 teams, there are 4 locations, mileage is given, no routes are forbidden. So all we have to do is plug in the numbers effectively and solve the problem accordingly. So what we'll do is we'll go to Module, and instead of transportation down here, we have a set method up here. It'll be slightly more difficult when we go to Excel, but for now in QM, click Assignment. We open a new file. We have jobs and machines. In this situation, they use the term machine. which isn't necessarily correct because we're not talking about machines in our situation. But let's go with jobs. We have 4 jobs: Raleigh, Atlanta, Durham, and Clemson, and we have 4 machines. Now you'll see here, we can be short of machines. We cannot be short of jobs. As the number of jobs changes, the number of machines changes as well. Sometimes we don't have enough people for every job. That's possible. Sometimes we have too many people for each job. That's also possible. We use the most efficient situation. But we can never have more jobs than people. If we have nine people or 9 machines, 4 jobs, if we change it to 5, it will automatically reset to 5. Because it is not possible to have more or less jobs than machines. That's how these problems work. So we'll call it the basketball official problem. And we have 4 jobs, 4 machines, 4 human beings. It's a minimization, as always, because it's a transportation problem. We hit OK. So machine number 1, now they've reversed it, but it doesn't really matter. In this situation, we'll say machine number 1 is Raleigh. 2, Atlanta. 3, Durham. 4, Clemson. Job number 1, Team A, Team B, Team C, Team D. All we have to do now is enter our mileage. 210, 90, 180, 160. 100, 70, 130, 200. 175, 105, 140, 170. Finally, 80, 65, 105, 120. Now, like I said before, we don't really have any idea if our answer is correct. Maybe we've made a mistake. Maybe the situation is much more complicated than the problem I've outlined in front of you. If that's the case, if it is more complex, then what we have to do is we have to take that into account, and we have to have a look to see what we think is going to be correct or incorrect. So let's look here. Team A is very short to Atlanta, but everybody is very short to Atlanta. Now let's look, and we see that everybody is short to Atlanta and everybody is longer everywhere else. So there's no clear-cut choice in Atlanta. 15 kilometers, 40 kilometers, 55 kilometers, 55 miles. So in this situation, what we'll do is, because we have the numbers over here, we're going to hit solve. Let me make this a little bigger. What we see in our results is Team A will be assigned to Atlanta. 90 kilometers, that makes sense. This is double, almost double, and more than double. So it's very efficient for them to go there. Team B will be assigned to Raleigh. 100, 70, 130, 200. It's the second closest, so that kind of makes sense. Team C is assigned to Durham. It's 140, but that's the second closest for them as well. So we have closest, second closest, second closest. And Team B, Team D will be assigned to Clemson. And that's a little strange because it's the furthest away at 120 kilometers. But 120 kilometers compared to 90, 100, 140 is actually quite close. So we can see that our answer is almost 100%. We're almost 100% sure that our answer is correct. In this situation, we're sending one official, Team A to Atlanta, Team B to Raleigh, Team C to Durham, Team D to Clemson. And our optimal solution value is 450 kilometers. That means that our team officials in total will assign one official to each game. Each game will receive one official each, and our minimum total travel time is, our total travel distance is 150 kilometers. 450 kilometers. Again, this is an intensely easy solution if we're using QM because there are no complications in this problem. So let's take a quick break again while I load Excel. Hello everyone, welcome back. In this section, before assigning a homework problem, I'm going to solve an assignment problem one more time using Excel. So we'll make our columns a little wider just for now. And again, basketball official example. You'll see that this is entirely the same as using a regular transportation problem. There is no difference whatsoever. The only difference is our supply and demand will equal 1. So, as before, let's begin with game sites. We're essentially recreating this table. We have Raleigh, Raleigh, Atlanta, Durham, and Clemson. Officials, Team A, Team B, Team C, Team D. Now we're going to put one more time demand, and as stated, the number is always 1. We also have supply. Each of the official teams exists only once, so supply is also 1. In 10 seconds, or essentially in under a minute, I was able to enter all of the relevant information. We'll add a few more, which is officials, and down here, officials. Equals sum of these 4. Fill right. I'm doing this as fast as possible because we've seen it a lot and I want you to see how quick it is to do. I could do it faster even, but I'm trying to give instruction as I do it. So sum of these 4 again, close it and fill down. We've entered all the relevant information now. We're going to come over. I'm going to make my columns a little smaller. So again, slowing down, but basically this entire problem could be solved in under 2 minutes. When you are comfortable with it, it's a very easy solution. So one more time, we'll do game sites. Raleigh, Atlanta, Durham, Clemson. And officials, A, B, C, and D. All we have to do is enter our relevant data, 210, 90, 180, 160. Again, 100, 70, 130, 200, 175, 105, 140, 170, 80, 65, 105, 20, and then down here, we're done. We have to enter one more thing, which is total miles traveled, and that's sum product. This array multiplied by this array, and we're finished. So even with explaining, I was able to complete this table in several minutes at the absolute most. If we go into our data function again, I'll go very quickly, but thankfully you can watch the video if you are unclear, or contact me and hopefully it will give you more information. So we go data, solver, our solution is found here. It's a minimization. We're changing these cells, same as before. We add two constraints. Oh, no, I didn't erase the first one. So add the first constraint is the number of officials must be equal to this. We add that. And one more time, the number of officials must be equal to this. Okay, simplex LP, solve. We see that we get the exact same answer. Team A is going to Atlanta, Team B is going to Raleigh, Team C is going to Durham, Team D is going to Clemson. So in under 2.5 minutes, if you've been doing the homework, if you've been following along, you see now how easy these problems are. So I'm going to wrap up the lecture because you do have another homework problem. The homework problem will be posted in our group chat. It must be submitted before class next Thursday if you want attendance for today. I will remind people, I have not checked attendance for the last several weeks. I've just been giving everyone attendance, but I do have a record of all your homework assignments. If you're not doing the homework assignments, you will not be counted as present. Please be aware of that. All right, everyone, thank you very much. And hopefully, if you do have any questions, as always, you can contact me. I will include the homework assignment in when I upload the links to our class.